Assalamualaikum and good morning. My name is Liana Amrani binti Mustafa Kamal, and in this video, I will be presenting regarding thermal conductivity and specific heat capacity of insulation materials at different mean temperatures. This journal is written by Y. Yosefi and F. Tariku and published on 2021. Alright, let's have a little introduction regarding thermal conductivity and also specific heat capacity. The thermal conductivity of a material at a point is defined as the ratio between the density of heat flow and the magnitude of the thermal gradient in the direction of the flow, while the specific heat capacity determines how much heat energy is absorbed or released depending on the temperature difference and mass. Thermal conductivity and heat capacity are among the most essential properties of a building insulation in calculating thermal performance, which are subjected to change when exposed to temperatures variation in service. Alright, let's look at problem statement. For problem statement, we can look at buildings account for nearly 40% of the global energy consumption, of which 85 to 95% is for building operations. Using building envelopes with efficient thermal performance help to prevent heat flux with the surrounding through the envelope and conserves energy. Consequently, less operational energy is required for space cooling in summer and heating in winter. Therefore, the application of insulation in building envelopes is considered as a simple yet highly energy efficient approach that can be used to residential, commercial, and industrial sectors. The thermal performance of a building envelope is governed by the thermal properties of its constituent materials, including the heat capacity and the thermal conductivity. Next, the objective of this study is to study the temperature dependency of thermal conductivity and specific heat capacity of commonly used insulation materials at extended mean temperatures below and above the current standard conditions. The study analysis revealed that the thermal conductivity in mineral fiber insulation increased at higher temperatures. Investigating the thermal performance of highly porous fibrous insulations, radiation and gas conduction as the primary components affecting the heat transfer in fibrous insulation, which both increase with temperature, whereas conduction through the solid has the lowest impact on heat transfer. Since the radiation properties vary with wavelength, the radiation component can be expected to change considerably with the increase in temperature difference. This phenomenon is one of the factors which cause the thermal conductivity in low-density materials to be more sensitive to temperature difference. Next, for research methodology, for experimental measurement and equipment, there are various types of insulating materials that have been selected to investigate a wide range of commercially available insulation materials for buildings in this research. Therefore, samples of expanded polystyrene insulations, or EPS, extruded polystyrene insulation XPS, polyisocyanurate insulated shading board, POLYSO, and mineral fiber stone wool were used. The thermal conductivities of building products were determined using the heat flow meter. The HFM apparatus establishes a steady-state one-dimensional heat flux through a test specimen at constant but different temperatures. Thermal conductivity is determined upon achieving thermal equilibrium and uniform temperature gradient throughout the sample. The general principle of the HFM is based on the Fourier's law of heat conduction, where Q is the density of heat transfer, lambda is the thermal conductivity of the material sample, and delta T is the temperature difference. The calibration factors was calculated for each designated mean temperature using heat flux transducers outputs from both planes of the HFM. The specific heat capacitor of the tested materials was measured using the Lasercom FOX600 HFM, which has an ability to measure the thermal conductivity of material. For specimens preparation and test conditions, 4 square-shaped samples of each tested insulation materials with a dimensions of 300 × 300 mm were cut preferably with maintaining the original thickness of insulation products. The selected samples were kept at normal lab conditions for an adequate period of time, which is approximately at least 6 months, before test to meet the testing method instruction. It was necessary to smooth the surface of sprayed foam polyurethane and cellulose fiber samples to achieve uniform plate-to-specimen thermal contact. Therefore, rough and uneven surfaces of one of these insulation samples were removed while maintaining adequate thickness for the test. Thermal conductivity as a function of temperature is an empirical relationship based on experimental data. Therefore, it is essential that a range of Therefore, it is essential that a range of temperatures suitable to the material should be employed in order to determine the function lambda. In an appropriate range of temperature, it is important to test at enough mean temperatures. Thus, in this study, the thermal conductivity of each selected sample was measured at 7 different mean temperatures, which are 5 degree, 10 degree, 21 degree, 24 degree, 35 degree, 50 degree, and 60 degrees Celsius, with temperature difference of 20 degrees Celsius. For specific heat capacity, larger sample with dimensions of 600 mm times 600 mm were prepared following the same procedures as for thermal conductivity measurement. In this study, the set points for heat capacity measurements were selected as 16 degree, 18 degree, 20 degree, 22 degree, 24 degree, 26 degree, 28 degree, 30 degree, and 36 degrees Celsius, with steps of 2 degrees Celsius and 6 degrees Celsius. The time for each measurement to reach the steady state of full thermal equilibrium varied depending on the size of temperature step, thermal diffusivity of the specimen, material thickness, and the amount of energy that was stored in insulation sample. By selecting 2 degrees Celsius steps, it took 4 to 5 hours for each temperature set. Now, we will look at the result of this research. The result of thermal conductivity and specific heat capacity tests of insulation materials at designated temperatures were plotted against temperature in separate graphs. Additionally, basic physical properties of tested insulations and a summary of their thermal conductivity results along with the results of the latest square regression analysis for each tested insulation material are tabulated. The thermal conductivity of cellulose fiber, EPS, SPX, open cell sprayed polyurethane and mineral fiber insulation samples increases upon rising mean temperature. According to the results represented in the table, as the mean temperature changes from 5 degrees to 60 degrees Celsius, the thermal conductivity of open cell sprayed polyurethane foam and cellulose fiber insulation increases by 29.2% and 18.5%, showing the most and least sensitivity to the temperature changes. With the same temperature range, the thermal conductivity of EPS, SPS, polyso, and mineral fiber increased by 20%, 23%, 21%, and 20% respectively. These results show how the degree of variation that temperature can have an impact on insulation thermal conductivity, which cannot be disregarded. Except for polyso, the curve fitting of the measurement points yielded a linear regression model with correlation of coefficients R squared, values between 0.96 and 0.98. However, unlikely the other insulation materials, the thermal conductivity test for polyso insulation board at different mean temperatures showed a non-linear trend with rising temperature. The thermal conductivity in all 4 polyso samples reached to its lowest point at 21 degrees Celsius, while increased at other tested mean temperatures. This nonlinear behavior of thermal conductivity is due to the effect of the blowing agent inside the microstructure of polyso. At lower temperatures, it starts condensing, which causes the increase of thermal conductivity. The measured specific heat capacity of all tested insulations presented linear upward trend by rising temperature. Upon increasing mean temperature from 16 degrees to 36 degrees Celsius, the maximum overall rise in heat capacity was observed for cellulose fiber samples as 11%, while the minimum increase was noted to be less than 1% for EPS and XPS insulation boards. However, compared to other insulation materials, cellulose fiber and mineral fiber showed less fluctuation in measured heat capacity through different mean temperatures. In contrast, the results of specific heat capacity of polyso insulation board reflected non-linear relationship with rising temperature. Lastly, for conclusion, in this study, the impact of mean temperature on thermal conductivity and heat capacity of 6 different insulation materials were investigated. Thermal conductivities and heat capacities were measured at different operating temperatures using heat flow meter apparatus. Analyzing the results showed that, except polyso insulation board, the thermal conductivities and specific heat capacities of all other cases increased linearly with rising temperature, where the curve fitting of their thermal conductivity measurements points yielded a linear regression model with correlation coefficients R-squared value higher than 0.96. For polyso, however, the curve fitting of the thermal conductivity measurements resulted a nonlinear regression model with R-squared of 0.97. Insulation materials are often advertised with a fixed thermal conductivity value, which is usually measured at 21 degrees Celsius to 23 degrees Celsius. Therefore, using a constant value for conductivity of insulating material is overestimated or underestimated heat flux in building envelopes through different seasons exposing different climatic conditions. Considering linear thermal conductivity for insulations allows more or less realistic heat flow calculation through the building envelope, since their conductivity in most cases increase and decrease at higher and lower temperatures. The author believes that more experimental research are required to determine the thermal conductivity of different insulations with various moisture contents at more extreme temperatures. That is all from me. Thank you.